Good afternoon. Welcome. My name is Anand Venugopal, and I head the product business for this product called Stream Analytics at Impetus Technologies. I'm really glad you're all here, and I think you all should first of all get a reward for being here post lunch and day 3. Clearly, you have some commitment that's bringing you here. So, and I can't believe another of my colleagues is going to speak at 4:10. I'm looking forward to see how many people show up at that talk. So, in any case, I'm sure there's a good reason why you're here. Really, thank you for being here. Thank you for your time and your attention. I have my colleague Puneet Shah here, who's a solution architect for Stream Analytics also, and we're going to be talking about this topic here, right? Lego-like building blocks of Storm and Spark streaming pipelines for rapid IoT and streaming analytics application development. I think the topic is fairly self-evident in what it is all about. It's an attempt to share some learnings and approaches we've created over time. We've been doing streaming analytics implementations for large enterprises since about 3-4 years now. And when we started, in fact, building a platform together, there was no streaming at all in the Hadoop distributions, in any Hadoop distribution. So we literally went out selecting Kafka, RabbitMQ, Hadoop, Storm, Spark, all of that. Spark wasn't even there at that point. So that's been the evolution of the product, Stream Analytics, which we are using as a tool to illustrate the concept that we're talking about today. We're saying, this is not rocket science, it's very, very simplistic concept, age-old, time-tested reuse of code. But in a visual paradigm, it's very, very interesting, and it has a lot of promise, we think, for the future. And if those of you who are actually streaming analytics application developers, it's going to be really, really useful for you. So, how many of you are in fact using Spark streaming today? Raise your hands, please. Okay, that's 1 out of like 25, 30. How about Storm? Is there anybody who's using actual Storm today and are looking to use? Okay, got it. And would any of the rest of you that didn't raise your hands volunteer on why you're here or what you're interested in? Any inputs there from the audience? In fact, I really want to make this interactive. So just given the advantage of a light audience, we can make it conversational, right? What did you find interesting about this topic? Any answers on why you chose to come to this talk? Lego? Good. It's part of it. What else? How does it relate to your job?
Basically, it's an IOT implementation. So you're streaming events, and you use one of the processes in line. See the ones that you create.
Right. Okay. Super. Got it. Thank you. So let's get on with the show here. A lot of people have spoken sufficiently about the growth of IoT and streaming analytics. Depending on what report you read, there's going to be 30 or 50 billion devices by 2020. There's an awful lot of devices emitting data. So there's going to be a tremendous amount of application development to harness all of that data at the core in terms of analytics. To make sense of what's going on and to leverage that and to get insights and to take actions. And of course, in terms of revenue, it's about 660 billion plus. I just want to set that context because that's what drives all of the development, and that's what makes it necessary for having some kind of easy, intelligent approach. So if some of you are wondering, and I get this question a lot, on what are the use cases in different verticals? Are some of you puzzled by what are the use cases for streaming analytics? Anybody? Have you wondered? You think that there's not enough? So why I'm asking is because I'm very excited about streaming analytics and its transformational paradigm of really altering business. And we think we've seen a number of use cases. Almost in every vertical you can think of, there are really good use cases to leverage streaming analytics and to make use of it. These are some of the ones that we are working on. There's a couple more of slides of this. So look at this, right? Retail, healthcare, manufacturing, advertising, transportation, logistics, gaming, telco, e-commerce. All of them have use cases that are powered by streaming analytics. And in terms of business value, it's being either protecting revenues or protecting your assets or increasing your efficiency or giving you opportunities for completely new businesses, new service offerings. And in terms of horizontals, we come across this pretty often as well. Customer experience, clickstream analytics, context-sensitive offers and recommendations, call center analytics, we get that a lot. Security and business activity monitoring. And the combo of when I call combo, I mean verticals and horizontals, right? IoT, mobile app, call center, they're all horizontal and they have verticals inside them. So all of these are, again, rich in real-time use cases. The way enterprises are going about the adoption of IoT and streaming is what we're seeing. There's insurance companies, we're working with retailers, we're working with e-commerce players, we're working with automobile vendors. One department somewhere in the enterprise starts this use case and does one, right? So if you're doing Spark application development or any application development in one enterprise for one application, you're cool. You can do it any way you want. You don't need tools. You don't need to scale it. And if that kind of a siloed approach were led into a much more heavy adoption of multiple departments doing multiple use cases in streaming, what is likely to occur? In an enterprise, even in single teams, we see now, at least there are some companies that are ahead of the curve that are actually doing many use cases. So we see the same data coming in, many developers working on the same data, having same data processing needs and patterns. So if one team went ahead and did, let's say, a fraud analytics application for a particular credit card product, and another team wants to do the same thing for another product, there's going to be small changes to that application for the product B. What do you think they would do? I mean, if they wrote the code in a monolithic way that was not scalable, that was not modular, they would end up wasting a lot of time trying to recreate that whole application where they could have easily reused some of those blocks that the other team did. So as adoption increases significantly, that's when you really need an enterprise-wide scalable approach, which it implies that you have a unified, multi-tenant, visually attractive, visually easy to use platform and collaborative reuse of components. And the reuse part is what we want to talk about, right? So the reuse of components to help you develop faster and get to many more applications much faster happens at 3 levels. So functions, which has always been around, right? You have basic ETL functions, date, string, integer manipulation, a lot of atomic functions which act at the field level, data level to manipulate the data. So whether you're doing Java code on Storm or Java code on Spark or Python, you have functions that you can reuse. You create functions, you reuse them across a team. Obvious, nothing new. Second, at the level of operators. So we're increasingly getting to a visual world where a lot of tools are having visual operators. So there's, let's say there's a visual operator for Kafka input. There's a visual operator for writing into HDFS. There's a visual operator for running a linear regression algorithm. So those operators, again, you could reuse and connect and build an application really quickly. We found that we can actually take that abstraction even one level higher, which is entire pipelines being reusable, right? So you could have a Storm pipeline that you use for, let's say, an ETL job. You could use a Spark streaming pipeline for, let's say, a machine learning job, or let's say for to drive a real-time dashboard. Could you reuse entire pipelines, connect them together like operators, and build an application really quickly? The answer is yes, and that's what we are really excited about. And why would you do that? Because there are reusable design patterns in stream processing that you're bound to run into, right? Anytime you have an IoT stream coming in or a non-IoT streaming case, such as financial transactions or clickstream traffic, there's going to be, first of all, your ingest problem. And believe me, Hadoop ingest is one of the most low-hanging fruits that we come across everywhere. Everybody's just basically trying to solve the ingest piece. People are using NiFi, people are using Flume. They just need a scalable, robust solution to get data in and land it into HDFS, right? That's just a starting point in streaming, we think, because a lot more intelligence is available in that streaming data. So ingest, if you get deep into each of these, there's so many functions inside of ingest. You need a Kafka channel. You need to duplicate the data. You need to eliminate noise. You need to do some transformations. You need to potentially, in some cases, resequence the data, filter the data so that when you get to the analytics stage, you're only getting the fields that you care. So that set of tasks that processes that stream is a pipeline. And that pipeline, if somebody does that, and if my partner has done it yesterday, why would I do it today? So I bring in the ingest pipeline, connect it to, let's say, the next pipeline, which is anomaly detection. Instant anomaly detection. And that's, of course, valid in security breaches, fraud, costly failure scenarios, predictive maintenance. In so many variety of use cases, you have anomaly detection that you need to do. And that's typically an event stream processing task. Similarly, we know some of our friends in major enterprises are using a Storm pipeline to classify the traffic first, right? There's a lot of traffic coming at you, and they logically belong to different downstream applications. You first classify them, put them separately into a different Kafka topic each, and you send out three different Kafka queues out into different subsystems. So that could be classification. That could be a block in itself. So similarly, there could be rules-based alerting. Every streaming application would have rules-based alerting and action triggers. Enrichment is one of the most powerful things we have ended up building. And this is all about taking streaming data, picking out fields from that, using maybe a key value, to go dip into a HBase, dip into an RDBMS, pull out a customer record, and enrich your streaming data, and then make a rich, insightful decision on that. So enrichment of streaming data with your static data, adding to the context, and taking decisions based on that is a very, very oft-seen pattern, and we've actually created operators around that as well. One of the most common things that everybody does with streaming data is time window calculations, right? So you could have rolling windows, you could have fixed windows, you could have staggered windows, you could have a lot of time window calculations with a time series database underneath, and maintaining those windows, performing min, max, average, variety of different calculations, and storing those, visualizing it, etc. Again, that qualifies to be a block in itself. There would be storage needs you'd have, which is batch up the data, store it into HDFS, store it into an index, etc. You get the idea. So, and the last one is important as well, predictive model blocks, right? You could have linear regression blocks, you could have neural network blocks. When I say block, I mean a logical set of tasks that are composed together that can be reused again and again. So that's to give you a sense of why or what kind of design patterns exist that could be accumulated into blocks. One team does it, another team reuses it. And in a more visual way, and there's another point I want to make in this picture. So if you take those blocks, assemble it, connect them together, you essentially build up a whole new application. So if that was done, if all you needed to do was apply a different model or a different anomaly detection algorithm, why would you build this whole pipeline again? Get the whole thing, connect it up, change that model, make modifications, you're up and running, right? So efficient reuse gives you rapid application development capability. The other important task here, the other important nuance here I want to point out is, notice that the first block, we've labeled it as a low latency engine. We think in complex environments, there's going to be both low latency tasks as well as batch tasks that you would need to do. If there is even one task, if there is even one thing you need to do within milliseconds, and everything else is okay to do it in a few seconds later, even if there's one task that you need to do within 500 milliseconds, you need a low latency engine, which is capable of giving you a response time in tens or low hundreds of milliseconds, right? Now, do you have the capability to do complex pipelines, which has Storm pipelines leading into Spark, leading another's Flink engine, etc. today, easily, visually? There's no such tool. That's why we had to build one, because we see the environments are complex enough that need multiple engines, and that gives you the ability to apply the right technology to the right problem. Let's say you're stuck with only Spark streaming. Every task is a Spark streaming task, even though Spark streaming is probably inefficient at that. For example, the low latency jobs that I just talked about, right? So we think large enterprises really need the capability to run multiple streaming engine technologies and have a single orchestration platform to orchestrate complex jobs like this. So the upstream jobs of ingest, filter, classify has to be low latency so that you don't constrain the downstream tasks. So the low latency engine does anomaly detection, alert triggers, et cetera, and then index visualize. And then you have, just like the Lambda architecture forks into a speed layer and a batch layer, inside the speed layer, you're forking into low latency and high latency pathways, right? So this would be time window statistics, persist and visualize. This would be anything that you would run as micro batch, large, semi-large batch tasks that are still real time, but more near real time than millisecond level, right? Examples are retailers in Europe today are beginning to do repricing of commodities 4 or 5 times in a day instead of once overnight. You need a Spark type micro batch engine to do that, right? A car rental company was looking to do the same thing. So maximizing and optimizing revenue with real-time inputs based on who's buying what and what are the various factors that affect your pricing. That would be the micro batch type scenario, right? There are other advantages in this. Notice there's one more thing I've said here, dynamic routing. Now, if you were able to route traffic dynamically in all these pathways, suppress one, stop the other, or do 50-50, or then do 100-0, et cetera, and you were able to do that with the click of a button visually, now that would give you the ability to do multiple things. Let me show you what that would be. A/B testing. So you have a fraud detection model, and somebody else says, "Oh, I got a better model. I think I can do this better." And another data scientist comes up with model B. So you create 2-3 pipelines. One is the ingest, filter, classify, all the stuff that you need to do upstream, common tasks. You fork the traffic into model 1 and model 2. Somehow, select by region or by time or some rule which you can split the traffic with. Test both the models at the same time. See which one works better. And once you know that model B works better, switch the traffic dynamically to model 2, and essentially you're implementing a champion challenger paradigm there, which is constantly you are calculating, you are learning from new inputs, more and more better, accurate models. And the moment you know that a model is better, switch it. And we can do this automatically with Zookeeper. Orchestrating, let's say, model learning is happening in batch, and you can switch using Zookeeper on the dynamic pipeline to get better models in place. No shutdown, no stop. It just continues seamlessly. Let's say a more simple scenario like hot swap. Today, you find a few bugs in your application, in your real-time application. Given it's real-time, given it's 24/7, you can't just turn things off. It's always on. So what do? You need a non-interruptive way to switch your application. So model 2 could just be your version 2 of your application, where you're just going to switch all traffic to model 2. And there you have essentially a new version 2 of your application up and running without any downtime. That would be some of those paradigms that are used, that are benefits of some of this topology, of this way of laying things out. I want to show you all of this in reality. We've actually implemented some of this with a couple of examples. We'll show you that with a demo, and Puneet is going to take over for that.
Thanks, Anand. Hi all, I'm Puneet. So I'll be demonstrating a live use case on movie recommendations. I'll be demonstrating the champion challenger behavior, how easy and visually we can simply swap models, drive the traffic from one model to the other. All of us are familiar with video streaming services like Netflix. The moment we log into Netflix, we see a recommendation of movies that Netflix thinks we would personally like based on our choices, based on our preferences, based on our browsing patterns. I've created a simple web application which tries to resonate a similar kind of behavior. The moment I log in, I see a series of movies out there in front. The moment I rate any of the movie here, the click results into a Kafka message that's published to a Kafka topic. What's going to happen is here we see 4 different pipelines which are connected together. The moment I rate any movie, the Kafka message lands onto the input pipeline right here. This input pipeline is essentially a Spark job which is receiving or reading the data from the Kafka topic. Let's take a look at that particular job, what it does. It reads data from Kafka. After that, we do some kind of enrichment. That is, we pull in the information about the user who's just rated the movie, what the browsing pattern of that particular user is, what are his preferences, what kind of genres of movies does that user like. So we fetch all of that information from HBase and Elasticsearch. That's the part of the enricher component. And after that, the router component looks at the rules that are configured to figure out where this enriched message needs to be sent to. In the current configuration, the enriched message is going to go to 2 different pipelines. We have 2 parallel pipelines called PPMF and ALS. Both these pipelines are recommendation algorithms that can take in the user data, provide recommendations based on the user's preferences, their browsing patterns, etc. Both these algorithms can also do real-time learning. That is, as more and more streaming data keeps coming in, these algorithms keep upgrading themselves so that they can recommend more effectively and more closer to what user behavior really is. Once both these algorithms will do their own respective recommendations, the outputs from both of these algorithms shall go to this final pipeline on this graph here, which is the output pipeline. Purely for a demonstration perspective, I have created these 4 pipelines, of which 3 are in Spark while 1 is in Storm, to demonstrate how easy and convenient it is for us to interconnect pipelines running on different clusters of different topologies. Right? Let's take an example here. So, well, Jungle Book's one of my favorite movies, so I'm going to definitely give it a 5-star, something that I grew up watching. The moment I gave a 5-star, it resulted in an event that got generated, got published to Kafka. That particular event went through both those algorithm models, PPMF and ALS. Both of them had their own independent set of recommendations, which they streamed out to the last Storm-based pipeline that was there in the graph right here. Let's take a look at this particular pipeline. This pipeline is getting the recommendations again of a Kafka topic. It's enriching those recommendations by adding additional attributes like the name of the movie, the release date, the IMDb URL, etc. And those recommendations are being streamed to the user on the web using WebSockets. So those are the results that we see here under ALS and PPMF. Now, as part of champion challenger model, I have got outputs from 2 models, and I need to figure out which of the 2 is the one that's more relevant to the user. Let's say PPMF is the one that's more relevant. Now, that means that I've already selected my choice of algorithm. It's going to be PPMF. This in turn would mean that all the traffic that's being driven on the web, wherein a user is browsing movies, the user is rating the movies, all that traffic now needs to be sent only to the PPMF algorithm. In order to drive all the traffic to this algorithm alone, I have a couple of options. I could select the path that connects the input pipeline to the ALS and simply just remove it. If I remove that path, that means no traffic is ever going to go from input to the ALS pipeline, and ALS will be essentially stop working. It will be more like taken out of the entire picture. Or if I want to do more of a dynamic routing, wherein let's say I want to use ALS algorithms during certain times of the day, or if the messages, user messages are coming from a particular region, then ALS is a better fit versus PPMF. I could do those as well. So essentially, in other words, I could set up my dynamic routing rules right here on the UI. So I need not go ahead, write change any code, restart pipelines. None of that would be needed. All I got to do is create my routing rules for dynamic routing of the tuples from one pipeline to the other. Right now, I'm going to simply delete this and click update. Now that the pipeline path has been deleted, I'll go back, I'll refresh this web page here. Again, select Jungle Book with 5 stars. And we see algorithm recommendations coming only from the PPMF algorithm, whereas from ALS, there are no algorithm recommendations at all. So essentially, as this entire screen, every operator or every pipeline here, which looks like an operator, is essentially a block in the entire scheme of things, wherein we can drag drop each one of them independently, each pipeline doing its own specific role, and we connect them in an order which makes sense to solve a particular business case. So imagine you had another business case where you wanted to use the PPMF or the ALS algorithm. You could simply drag or reuse the same pipeline in that particular use case itself. A developer would not have been required to go through the entire process of recreating those algorithms, making them compatible, or even take another example, any algorithm needs enrichment. So the input pipeline that we had earlier, which was doing enrichment of the data, that too could be reused. Data cleansing, data quality checks, all these kind of functionalities could be built in or manifested into simple individual pipelines that could be reused again and again for solving multiple business use cases.
So actually, let's just show them another example of assembling an application, right, together with those components. We actually talked about one application on the presentation. So if you were a developer, you had the case that we showed on the presentation to build again. You would just drag and drop an ingest pipeline. So we're going to build another pipeline, right? So just drag and drop an ingest pipeline. The ingest pipeline would essentially bring in data, filter it, etc. And your anomaly model is already ready. Somebody else has built it. You're going to take that, connect it, and like I said before, that could be Storm, and you could route the low latency traffic into the anomaly detection algorithm, and you could parallelly create a pathway to do time window based enrichment, and finally do storage and visualization with another module. Right? Each of these is again whole pipelines in themselves. Can we click and see what they are? Okay, yeah. So for example, that last one is a Spark-based pipeline which takes in Kafka data, stores it into Elasticsearch, also does parallel storage into HDFS, and streams out into a WebSocket. Right? That's a whole pipeline in itself. Rather than building complex, monolithic, huge pipelines on Storm or Spark streaming either way, we encourage essentially to build smaller pipelines, modular tasks, and then reuse them, because we've actually done the other way before, which is build humongous big pipelines. Even though it's visual, even though it's so easy to manage and understand, it can get pretty unwieldy. So this could be another way and efficiently of doing it. And like he did earlier, with the press of a button, you could redirect all of that streaming traffic onto a different model or doing dynamic routing. So if that application was live in production right now, imagine the scale of what you're accomplishing with one click, right? All your web traffic, all your recommendation engines now literally going into another module, another pathway, and with a click of a button, you just achieved such a huge DevOps task that would probably take hours of labor and coordination and integration otherwise. So we just wanted to present this approach to you, and that pretty much concludes our demo here, and we're open for Q&A on this topic. Thank you. We have 11 minutes to go, so if you have any questions, Storm, Spark streaming, anything at all, please go ahead. Yeah.
It could be any messaging queue bus. So it could be Kafka, it could be anything which is JMS based as well. But it has to be a messaging queue in between, because the upstream and the downstream pipelines could be operating on different speeds. So you need some. Yeah.
So here you just drag and drop two pipelines.
Correct.
Connected, right? So what happens behind the scenes?
Sure. So this router component plays a major role in determining what's the next destination and what the next destination looks like. So the router component has rules configured that too you configure on the UI. So the router component evaluates those rules to figure out first what's the destination or the target pipeline it needs to send the incoming tuples to. It could be one or it could be more. Based on the target pipelines that it identifies, it looks at what those target pipelines are reading data off. If those target pipelines are reading data off Kafka, it would push it to Kafka. If they are reading off some GMS-based queue, it would push it to that system.
And there's got to be data compatibility between the two, any two things you connect, right? Suppose you're emitting name out of here and you're expecting, age out of there, that's not going to work. And in fact, that level of validation we do. So you can't just arbitrarily connect anything. There's got to be, the pipelines have to be emitting and expecting the same data.
Same schema, essentially, yes.
Yeah. Please be louder.
The rules that you showed when you were routing, what did you use to write those?
The rule engine, meaning what's the rule engine that's powering this? So we are using MVL expression library, which is powering these rule engines. So that's how we evaluate the rules that the user chooses on the UI.
So you're using ML. ML is the same thing that's used in Ruby, right?
Correct.
Yeah.
For your dynamic rules, do you have anything that, like an API for programmatically changing those, like let's say from a different machine learning algorithm, running to determine which model should win in particular cases?
So we use Zookeeper for all of that. So all the dynamicity is brought in by Zookeeper. So we have watchers set up there. The moment anything changes, those Zookeeper watchers get triggered, and then they know how to tell the router component whom to route the appropriate messages to.
So yeah, programmatically it's possible to do that.
Is anything done in terms of resource management or automatically scaling the infrastructure underneath and or as needed, depending on the volume of messages coming through?
Right. So this particular demonstration did not cover that aspect. Right. But essentially, yeah, we do support scaling up or scaling down. So especially for the Spark pipelines, because Spark supports back pressure in the scale up version.
So it's all, it leverages the underlying infrastructure of Storm and Spark, and yeah, scale out is possible. In some cases, it's not automatic. That's enhancements we're working on, but we inherit all of the capabilities of the underlying engine. Yeah.
So today you support Spark and Storm pipelines, right?
Correct.
Any plans of supporting Apex or Flink?
Apex or Flink would be our third engine choice. We're looking at it carefully. We take a call based on overall industry adoption, and that definitely is on the radar. Yes, leaning towards Flink more than Apex. Any other questions? Thank you.
Thank you,
Thank you
everyone.
for your time.
Thank you.